All right, welcome to the Real-Time Digital Signal Processing Lab class at the University of Texas at Austin. This is Lecture 2, Part 1 on Introduction to Digital Signal Processors. What I show here on the slide are some three classic architectures for an embedded digital signal processor. And the architectures are really chosen to do high-speed arithmetic and also to, separate from this, we also have to support high-speed input-output. So this is the CPU core, and back in the first commercially successful digital signal processor was in 1982 from Texas Instruments. There had been some other attempts starting in 1978 to take some ideas from supercomputers and put them into embedded platforms. Those did not do very well commercially. But in '82, TI did strike some success, and this is the earliest architecture that's there. And it's Accumulator Architecture, and again, the idea is that back in this time frame of 1982, the primary and almost exclusive use of the DSP was to do arithmetic, and there was no operating system and no compiler. This means assembly language, and you're the only program running. Your program is it. You don't have to share anything with anybody. The whole processor and all the peripherals and resources are yours. So in this particular architecture, just to get some graphic notation here, this is the on-chip memory on the right here. So local on-chip memory, high speed, readable. The throughput of reading and writing to local on-chip memory is the same as the CPU clock, or the instruction cycle time, sorry, to be more precise. But on-chip memory was limited, and it was also dual ported, so you could do two reads in one memory cell at one time. So it was special purpose memory. You always had, though, to bring in the data through the accumulator. You had no choice, and this made sense because we're constantly doing multiply, add. So the multiply would be so either we bring it through the accumulator and add 0 to it to not keep it unchanged, or we put it in a multiply accumulate. So we might do a multiply earlier, and we might add something to it. So it just depended on how we brought it in. The accumulator was more than addition. It was addition with extended precision. So the idea is to keep the carry bit in the calculation. So if I'm adding 16-bit numbers, worst case, I get a 17-bit result. And so the accumulator was typically very long. Also, if I multiply two 16-bit numbers, I get a 32-bit result. And if I start adding two 32-bit numbers, I get 33 bits in the worst case, and so forth. So accumulators here were much larger than the multiply-add operation. So so in this particular processor, it was a 16-bit by 16-bit multiplier for TI anyway, and a 40-bit accumulator. So you could accumulate many multiplication operations before you hit the 40-bit word size. So now my question is, how many 32-bit numbers would you add together before you reach this 40-bit worst case resolution or precision? How many would it take? This is a great interview question on campus. If I want to add a bunch of 32-bit numbers together, how many do I add together before I hit a 40-bit, the 40-bit long word in this particular processor? I hear 7, I hear 16. You're thinking linear, I think. All right, so we'll do the adder tree again. The adder tree will come up a lot. Any other guesses before I go to the adder tree? It's a lot more than 16. Okay, so the adder tree. The adder tree is, if I add let's say 32-bit numbers together in this case, I get a 33-bit result, worst case. If I add two more 32-bit numbers together, again, I get 33 bits, worst case. Now I add those up, and I get 34. Okay, so I add two numbers together. We did this in the Mandrill demo, or if you're watching the video, we will do it in the Mandrill demo in Lecture 5, Part 4. Okay, so I get two 30-bit numbers, give me 33. Four 32-bit numbers, I need 34 bits. So when do I need 35 bits? How many? 8. So now I ask again, how many 32-bit numbers do I need to add together before I get the 40? 2 to the 8th, which is 256. So that gives you an idea of back at least in 1982 how long FIR filters were in those days. Right? 256 was a long FIR filter. By today's standards, no, it's not very long.
Wouldn't it end up being more because eventually you'd be adding two 32-bit numbers that would just barely make a 33-bit number on either end, and then you'd add those two together and still get a 33-bit.
You still might get a carry. So if you add, to get the 40 bits, adding 256, so again, this is add 2, I need 1 more bit, add 4, I need 2 more bits. Remember, I have 8 guard bits here. I have a 32-bit multiply result when I multiply 16-bit by 16-bit numbers. So I add, 2, I get an extra bit. I add 4, I need 2 extra bits. So it's a log base 2 of the number of terms that I'm adding. So if I add, 257 terms, I need 41 bits. Now this is about without loss of precision. I can certainly add all I want and throw out bits, right? So I have an option on the processor in lab. I can add 2 32-bit numbers and keep the result in 32 bits. Or I can use the long 40-bit word and keep the full precision. All right. So this is again 1982 time frame. I wasn't programming then. I started programming in 1987. So but they still had. I was still using this family. The spring of 1988 was my first time programming a digital signal processor, and we still had this architecture. All right. The next advance, if you will, was late 80s, early 90s. And this looks really old stuff because it is. This is an old view. So the next step was late 80s, early 1990s. Now you could bring in values directly from local on-chip memory into the register file for the CPU and back. You can move back and forth, load and store, if you will. And you could also go through the accumulator, which again was extended precision. Okay. So for just another processor family, the Motorola 56000 had 24-bit data type and 24-bit by 24-bit multiply, gave you 48 bits. The accumulator was 56 bits. So it was the same number of guard bits, 8 guard bits. Okay, so that's the memory register architecture. So we're making some progress. Finally, 1996, this is now the processor that you're using in lab, at least it's based on this architecture. Now we have load store directly, and you cannot do any work on data until you load that data from on-chip memory to a register. Then you can work with it. And when you're finished doing the calculations, you can store the result from a register back into on-chip memory. And that's the more common case today in processors. Now, also on your processor, the accumulator has, again, 2 flavors. You can do 32-bit accumulation to a 32-bit result, or you can do 32-bit accumulation and store the result in the 40-bit mode. So you have 2 options on your processor. Okay. Why did they choose 40 bits? Well, so first of all, it's to make sure you don't lose any precision. The second reason is there is and it's been a while since I've looked at it, there are some unusual cases in speech, one of the speech compression standards that required a 40-bit mode. Okay, so that was another. So I don't know. I think this came before the speech compression standard. So I don't know exactly which motivated which. But why the extended precision? Just so you don't lose the information. Right? In other words, it's like keeping the results in your calculator or MATLAB until you need it. Right? So you keep everything in extended precision, and then when you need it, you reduce it to 3 or 4 digits or whatever.
It just seems that they would have chosen a 16-bit or 8-bit.
Power of right, but another bit is a lot of extra power and transistor count and all that. So 40-bit was probably a pretty good compromise versus, say, 64. We're talking about 1982. Yeah. Today the processors, most of the transistors are for memory. Very little for the CPU core. So on the C6000, the very first C6000 just had 250,000 transistors. That's it, not a billion, 250,000, 250,000 transistors. So where's the rest of it? Well, it's in the memory, or you put multiple cores. Okay, so by today's standards, this isn't a lot of transistors. But in 82, every bit mattered, and also every bit means power, area power, right, cost. All right, so that's where we are today. So what I do today is more of an introduction to the digital signal processors, and we'll talk about signal processing applications for those processors. And today things are all jumbled. It's rare today to have a single processor, a physical chip that is just a single core DSP. More commonly today, you have multiple cores on the chip, and even not even the same core. So heterogeneity is a little more common today. All right, so we'll talk about the first two items in this lecture, and then part 2 is the C6000 family. And then part 3 will be pipelining and so forth. All right, so we talked about this definition early in the class, and this is just the operating definition for the class. It's not the only definition, and it's not comprehensive. It's just a working definition of an embedded system. So an embedded system works on application-specific tasks, and it's often behind the scenes, but that distinction has gotten blurred over time, where the program, the user now has a lot more accessibility to programming the processors. This is true on smartphones and so forth. In terms of context, where the embedded processors fit in, it's pretty remarkable. So the embedded processors today make up more than 99% of the market in terms of units shipped. So I always ask on our faculty, Professor Pat, who just got in the National Academy of Engineering, I ask him, because he doesn't work in the embedded space. I said, well, in the embedded space, it's 99% of all the processors shipped. In fact, it's 99.2%. And he goes, thought for a minute, and he thought, well, I'm happy working on the 0% of the market. So it's okay. All right, so so if we look at where this fits in consumer products, so this is really what's driving this, really almost from the mid-90s, was cell phones. So today this is 2002 data, 2012 data, sorry, 2013 is a little bit more than this, 1.9 billion cell phones sold last year, roughly. Okay, so the cell phones today are multi-core, and we'll talk about the iPhone in just a few slides, not just one core, many. Originally, there were 2 cores, a DSP core and then some microcontroller to handle the user interface. And that market's been increasing. For PCs, this has been kind of in decline. Tablets are often considered in this market space, so when they do consumer surveys. So the PCs are declining. DVD and Blu-ray players are, I couldn't get a sense on where they were headed, so it was pretty flat compared to 2011 to 2012. Same with digital still cameras. These are mostly point-and-shoot cameras. And see what's left. So declining are DSL modems, increasing almost by 10 million units, I think, versus 2010. 70 million cars and light trucks. This is just in 1 year, and 34 million game consoles. Now, so a few things are here. How many processors are actually today in a cell phone? And we'll see this. Any guess on an iPhone? How many CPU cores are in there?
Like independent chips.
Cores. Or 7, 8? 10. 10. At least 10. It's hard to, they don't advertise everything that's under the hood.
Encompassing like all 10 of them are in the same chip?
Nope. No, we'll talk about that. They're in multiple chips. Over multiple chips, but you have multiple cores on certain chips. Other chips are single core if they're special purpose, dedicated. All right, so 10 cores here. PCs, how many embedded processors are in a PC?
Usually.
A lot. So give me some examples.
You're going to have
Sound card?
You're going to have the motherboard
Video card?
CPU on the motherboard, then you're going to have your CPU on your graphics.
Embedded. So let's let the CPU alone. That's general purpose. It's there.
Yeah.
And multi-core and all that. But on the embedded side, where the user, again, is going to have little or no direct interaction with programming it or configuring it directly. So the sound card definitely has a DSP in it. Video card, has a graphics chipset, a little different. You could argue it may not be as embedded because that's programmable directly from the user, certainly. But certainly is in there. What other processors are there besides the general purpose CPU?
Hard drive motor control?
Hard drive motor control. For many years it was DSP until it went to solid state, and I haven't checked what solid state drives use. But prior to solid state drives, it was a high-end DSP with 16-bit or more word size. I use a 16-bit DSP, actually.
Any other peripherals?
Peripherals, yeah, so give me an example of peripherals.
USB, VGA, HDMI?
So USB, all the serial bit streams, all the serial lines on a PC, it's a communication system. It's a serial stream with a clock embedded. It takes a lot of signal processing to recover the clock and decode the bits. PCI Express, and so for all these lines have got very interesting communication systems all by themselves. So a number of communication system engineers over time migrated into this space. It has a lot of the same problems that we see in the wireless scenario or DSL or any of these. Wi-Fi cards. Okay, so initially these generations of peripheral control and interfaces will have programmable components on them just to get out to market faster. But with each generation, it can be more and more hardware to reduce cost, reduce power, reduce physical size. Okay, so eventually, after 3 or 4 generations, the programmable core has been replaced with mostly dedicated hardware, just for savings. Integration basically just down to one chip as much as possible instead of multiple chips. So these days, Wi-Fi, controllers are going to be, largely mostly hardware. So what else can you? So all the things that basically all the interfaces, almost all the interfaces have some sort of signal processing involved. Okay, so there's got to be some programmable processor in there, initially starting as a programmable processor and evolving with time into hardware implementation. Still cameras, depends on the still camera, but these would be multiple processors. You're going to have at least one to handle the real-time image acquisition, video acquisition, compression, enhancement, and at least one for all the system functions, and maybe more than that. So accelerators possibly beyond that for compression, hardware accelerators. So at least 2 programmable processors. DSL modems can fit pretty well in typically one processor, and that's kind of nice. So they'll just have, or one core, so they'll have multiple cores in a modem to support multiple lines for a company's deployment of DSL. Now, cars and light trucks, this one's how many programmable processors are in cars and light trucks? Hundreds. That's right, hundreds. It's amazing. So tell me where they might be placed in a car. Engine control. But what parts of the car? What subsystems in the car? So anti-lock brake systems, engine control, GPS, radio, air conditioning, power steering, navigation system. I mean, all these things, right? It's amazing. Hundreds. So if you look at the alumni list from the class, you'll see some of them going off into automotive spaces from this class, both under the hood and also in the cabin. So the processor you're using today in lab, the 6748, is in this OMAP family, this Open Multimedia Architectures platform. A primary application today that TI has been pursuing is the in the cabin or in the car automotive systems. This would be navigation, entertainment. That's the primary use today for the OMAP that you have for TI. Another side is audio, and we'll talk about that as we go, why that's useful. That will come up in a few slides. So, and I had this slide early in Lecture 0 with all these products that are based on DSPs, and that part of that's pro audio, high-end consumer audio.
Who's making the processes and all that are controlling like automated driving, like self-assisted, or like car assisted, like parking and all that? Like now all these like new cars have like these.
Yeah, I don't. Anyone have an idea on that one?
Wait, what is the question?
For automated driving and parking. So like self-parking or parallel parking, automated parallel parking is something on some cars. And I don't know the processors involved there. About any bids?
I imagine CPU for most of the programming and embedded system for handling the sensors and implementation.
There's certainly a lot of sensor data and sensor fusion happening, and then once you figure out that, then there's a control side of actually how you, in real time, park the car. Automated driving is a little more complicated, so it'd be the Google car or whatever. So it'd be, I don't know. That's going to be obviously more than one. Many. I just don't know which ones are involved. All right, game consoles. Now there was a decline in game consoles because at least in 2012, I don't think there was a major release of a game console but that changed a year ago. There was PS4, so this should be up again in 2013.
Where would you say Internet of Things applications are? So Nest and all the control power of your heat, cold, or refrigeration.
Right. So Internet of Things, absolutely need lots of embedded processors for that. These are these are units shipped in 2012, and it's going to be increasing things like smart grid communications, in-home energy monitoring, and diagnosis of what's using the most energy when. You also need processors when you plug in electric vehicle to a line, because there's different ways you can charge, different settings. It's a power line communication, an example. Absolutely, there's no shortage of. That's another boom to the internet. This is a machine-to-machine communication space, which is huge. So here I'm just really, these are consumer, these are things you would buy locally at an electronics store. So there's this whole other side of machine-to-machine communication not reflected here, and I don't have those numbers, but they're going to be huge. Okay.
Do you say that like ARM is basically spearheading these?
Yeah, ARM is a major player, so they've shipped more than 10 billion cores, and we'll talk about companies in just a second on the handout. They're a major player in this space. Okay, so we've kind of addressed how many embedded processors are in each, but except for the game console. So how many embedded processors are in a game console?
I think it's going to be
Same
kind of like
computer.
comparable to PCs.
Comparable to the PC, right? A lot of the same functionality, so it's pretty much the same answer. So it could be 10, 12, right? So for every GPU, for every CPU you've got in a PC, you've got a dozen plus embedded processors behind the scenes. You've got graphics processors and so forth, in addition to the general purpose CPUs. All right, now how much should an embedded processor cost? Depends on the application. So I give you, let's take an example. So let's take a traditional cell phone from 2011, $73 for the entire phone.
$7.
$7, right? How'd you get there?
Cores, 5.
Well, this is a traditional cell phone, 2 cores. One for the real-time stuff, speech compression, and so forth. This is 2G. Think 2G. Think old school.
That's retail.
Retail. That's the retail cost. So let's work backwards. What's the wholesale cost? Half of that. What's the manufacturing cost? Half of that. So we're now down to $18 to manufacture this thing. That's everything. How much of that is testing? The process, the part, half, something like that. 60%, depends on who you talk to. Let's go with half, which is generous. So now we're down to $9 in components and design time. Everything else is $9. $9. It's not a lot. So how much are you going to pay for your 2 chips for your programmable parts? Too much. How about 50 cents, $1, maybe $1 each? Maybe $1 for the DSP, 50 cents for the microcontroller. And the rest is going to be, keypad and display and all that. Small display. All right. Now let's take if you take a digital camera, a little more. Again, this is the average price in 2011. A little higher end cost. So now you can spend a little bit more on the processors. Again, the wholesale price, maybe it's $95. We'll call it, maybe $100 even. And manufacturing costs $50. Parts $25, including the engineering design time. Us working on this stuff. So it's not a lot. So maybe you're willing to spend $5 on a processor, 2 processors and some accelerators. Maybe you're willing to spend $10 total on all of that, or maybe less, because you've got the acquisition system, you've got playback. So it's not. Yeah. All right, 2012, the iPhone 5. This is without contract. This is the retail price. A little more. Now you can put in a lot more stuff. $749 and $849. I can put in some more stuff, a lot more stuff. So now we're down to a wholesale price of $400, manufacturing cost of $200, parts and design time at $100. Now we can do some pretty interesting stuff. Let's talk about that. So here's the iPhone 5. This is from a teardown on the web, and on this teardown. These are what they found from just taking apart an iPhone, and they give you the pictures, the play-by-play story as they go. So this is the cores they could find, and in the cores they could find, so they have the app processor, from Samsung, right? Or is 5 cores, so it's 2 ARM cores and 3 GPU cores. Why all the GPU cores? Graphics for what?
Touchscreen.
It's touchscreen and more. Gaming.
Principally.
Augmented reality. Other apps, absolutely. So the touchscreen has got probably 2 ARM cores. I mean, it's hard to know because you have to kind of figure out who's the manufacturer and what are they probably using. The audio part is done here in Austin. It's a Cirrus Logic. It's a DSP. 1 DSP core and 1 codec. So they do both the programmable part and the A to D and D to A converter. 2 chipset. 1 for that codec, A to D and D to A conversion, and 1 for the programmable processor. Wi-Fi is Broadcom, baseband is Qualcomm, initial sensors are STM Microelectronics. I also went and looked for a market share and for these different companies. So for the smartphone market share, it's for the third quarter of 2012. So it's 3.8 billion for just the application processors, and there are 2 different approaches to this. One's a standalone app processor. So if you have like the iPhone would use, then you also, for the iPhone, you need the app processor and the communications processing as well. So 2 different chipsets. The other approach is an integrated baseband app processor from Qualcomm, and that work is largely done in Austin and San Diego. So there's a design center here in Austin for Qualcomm doing the Snapdragon and other processors for smartphones. So I looked through the market share. The bulk here is Android does quite well. Samsung is also part of the Android, obviously, story. Samsung is part of both stories, both major stories at least, and other companies that come into play here: MediaTek, Broadcom, NVIDIA, and others. So NVIDIA is a GPU company. So what are they doing in this space? How'd that happen? There's a demand for it, but how'd they enter this space?
Tegra?
Go ahead. Yes, you got it. What happened?
Didn't they just make a CPU chip?
Yeah, they bought a company. They acquired a company that was in this space, and then kept going from there. Absolutely. Right. So tablets, as I said, are often put in the same market. At least here's now it's broken out a little bit. So here's 2012 tablets versus smartphones, and then the 2013 is estimated. When I put the slides together in December, I didn't have the data for 2013 yet. But what it does say is that 32% of the revenue of all microprocessors sold in 2013 is in tablets and smartphones.
We have Samsung under Apple.
Well, because back, this is 2012, right? So they're providing the processor for the iPhone. Again, this is 2012 app processor, and that's true. I have Samsung also separately listed as well for the Android platform. So they're in both. Okay, you're right. So this also. Who else makes processors for Apple tablets?
Doesn't Apple make them too?
Apple makes them. They have a design center here in Austin as well, when they bought Intrinsity. So there's multiple vendors, so maybe that should be probably more inclusive. All right, so let's talk about some applications and for the processors. So and this hasn't changed that much with time in terms of these different frameworks here. So either we have a single DSP, which is less common these days, although you'll still see them in sound cards and older, maybe more older stuff. And car audio today depends how sophisticated you want to get. If you want to go almost to pro audio, you're going to need more than one DSP. Guitar effects. So the processor you have in class, in lab, the 6748 is really good at guitar effects and mixing boards and other things. I guess we can talk about it now. So in in audio, what's a very common bits per sample?
Like 44 kilohertz.
That's a sampling rate, so 44 kilohertz, 48, 96 kilohertz, and so forth. How many bits per sample?
32.
32 is on the high end, 16, 24. So 24 is about the limit of D to A and A to D conversion today over audible, over those kind of sampling rates. You can read 32 bits, but really the 24, the 24 bits are accurate. Anything beyond that is not so accurate. It's mostly noise. So it's 24-bit audio, and so if you think about the 32-bit floating point data type, it's got 24 bits of mantissa plus sine. This is a perfect match for the 24 bits coming off an analog to digital converter. And then you have floating point, which allows you to scale 8 bits of exponent dramatically the number that you represent. It's more than just the 24 bits of mantissa. Now you can represent very loud and very soft sounds because of the floating point format. So it's ideal. And there's a paper in the reader on the use of the C6700 family, floating point 32-bit family for audio applications. In your reader, there's an article by Gene Franz and Ray Seymour on this, both from Texas Instruments. Okay, the next one up is medium cost, medium throughput. These would be, not quite the 4G today, quote unquote, but so 3G, DSL modems, video conferencing. So it's a little bit more. These are higher power consumption processors, and more than one. And then finally, the really high end in terms of cost and power consumption, which would be high cost, high throughput. Now we're into medical, big medical instruments, X-rays, tomography systems, and so forth, multi-channel audio mixing boards. So there's a whole range of where these things might be used, and cost, and physical size. But in this embedded space, we have some special requirements that are not so much there in the GPU space or in the CPU space. One is just expense. We need to get down to $1 or even 50 cents in volume. We want to have small area, and in volume means if you buy 1,000 of them, they should be, $1 or even less for some applications. There's small physical area and physical volume. They have to fit in a small place, and they also don't want to consume too much power. Because you're in a small space, there's only so much you can cool, and you like to avoid putting the fan in if you can to cool it down. Predictable input-output rates to and from processors. So if you've noticed in lab, we use interrupt service routines a lot to handle data that's coming in from off-chip, and also to put data out off the chip. So reading and writing from off-chip, this is important. And so your processor has a very predictable interrupt service routine handling latency latency and that's 11 cycles. It's the CPU itself takes 11 cycles to service an interrupt, and that's it. It's predictable. Now, if there's an operating system on there, there may be there's additional latency, but the CPU itself, 11 cycles, exactly. It's not random. So it's predictable in how you can get, and so as you move blocks of data on and off the chip, you know what it will take to service the interrupt for that data transfer. Low power. A lot of laptop and other processors have gotten better with this. We're talking in the below a watt power consumption for the whole system. So this is just some older Snapdragon numbers actually for this one. This is probably 3 years old, but you're in the hundreds of milliwatts for the whole smartphone, not watts in for a desktop. Lots of watts for a desktop. Okay, so here's a comparison of fixed point and floating point. This is, and we'll get to the handout next from Berkeley Design Technology. So the fixed point per unit cost, these have all come down. So it used to be floating point processors were much more expensive, and over time they've come down in price. So you'll see on this handout that the per unit cost now is down pretty low, down to $2 if you order 1,000. And of course, you can always get free samples of 1 or 2 if you call. Right? That's something that we do in the university a lot in our department. TI and other companies do this. Analog Devices does this. Where else have you gotten parts?
Maxim.
Maxim. So these are all, and there are many other companies that will do this too. to ship you 1 or 2 chips free. Now, the prototyping time is a big deal. So the cost is the part cost is important, but also how long does it take for the engineers to get something to work? And for floating point, the nice thing is what you do in MATLAB has a lot of connections to what you do. Now, there are some catches, of course, in memory and some other things. But because you're using floating point, it matches what you do in the C language with the float data type. And a lot of the C code that you can find online works pretty well. And it's easier to develop because you can compare directly against MATLAB simulation or LabVIEW or any other design tool. But for fixed point, now I have to convert designs into 16-bit integer. I don't have the scaling of the exponent anymore. I can get all kinds of crazy quantization effects. Power consumption generally a bit lower for the fixed point. Again, the word sizes are smaller. This is typically 16-bit, for example. And this is typically 32-bit, right, for the floating point. Power consumption is down. Clock speeds have come up on the floating point parts. We'll see that on the guide. It used to be floating point parts were much slower, but today they've gotten just as fast in some of the families, which is a bit surprising, again, because we have larger word sizes. Battery-powered floating point generally doesn't show up in battery-powered. Takes too much power. But they do show up when you have access to lots of power, either in a car or plug-in from the wall. So both pro and car audio and medical imaging. On the fixed point side, volumes are much higher. You're going into cell phones and digital cameras, so the number of units sold per year way more in the fixed point case than the floating point case. And lastly, prototyping time. Again, for the floating point, we can reuse desktop simulations. We also, in practice, use floating point DSPs sometimes as for the final product, but sometimes we use it just to prototype the feasibility. So sometimes we don't even know that what we're doing can work in real time. So the easiest thing to do is get a floating point DSP, because all the C code pretty much should run, and just to see if it's even feasible. Can we get even close enough to real time to justify the design time to get to a fixed point implementation, just an integer arithmetic? So the processor you're using in the lab is floating point. It can be used either directly in a product or as a first stage in going to a higher volume fixed point implementation on a programmable processor. One of the reasons why the design time is longer, just a few things, you have to convert floating point to fixed point, and just quantizing coefficients and calculations can lead to a system that actually fails. And we'll talk about this later, but in infinite impulse response filters, this conversion can cause a perfectly stable filter to go unstable. It can become Bibo unstable. You have to redesign the filters. You have to redesign the algorithm typically when you're going from floating point to fixed point. And in many cases, you'll use non-standard C extensions, like a fixed point format with a binary point. That could be, you have so many bits left and right of the binary point. This is not supported normally in the ANSI C standard. So there's a lot more effort in the fixed point side. Okay. So this I've covered. This will be part 2. So let's go to the handout for Berkeley Design Technology. Go ahead.
Just out of curiosity, your link to reader N is not working.
The link to
Reader N, reader handout N.
Okay.
I don't think it's working.
All right.
We tried it. I tried it.
All right. I'll check it. All right. So I'll check the link to make sure it's working. All right. So this is the handout on the back table, and this is from Berkeley Design Technology, and they are in Berkeley, California. And you'll see this. They've been doing this since they say they were founded in 1991, but they've been doing this kind of survey for about 20 years. This kind of pocket guide has been around a long, long time. It's every year they update it, sometimes twice a year. But there's some trends in here that are worth looking for. So I'm showing here part of that handout. So the top of it is this is called the pocket guide. Here it's a different title, but it's Independent Guide to Processing Engines and Embedded Applications. Sometimes it's just, let's see. There we go. All right, so there's two different parts of this handout. One is for chips, and one is for cores. All right, so what's the difference?
Core in the chip.
Cores in the chip. That's a good way to talk about it. Right? So a core is something that's is not delivered in silicon. It's delivered in hardware description language that can be synthesized. So the Verilog, probably more likely, or VHDL is another option. That can be synthesized directly into a custom design. The chips are what you buy, right? Physical chips. All right. So here are some companies that work in this space, and the number of companies has decreased with time. I'll tell you that. There's been consolidation in this business. So analog devices, first up, where are they located? You get your smartphones out on this one. We can put some DSP to use in the classroom. Beyond
Boston.
Boston is, yeah, it's a suburb of Boston. That is correct. So it's in Boston, Massachusetts. And they've been around since the early 80s. They bought AMD's attempt at DSPs in the late 70s and made it commercially successful. So they have they've been around a long time. They may make lots of different components. They're I guess, the leader in data converters in terms of I guess, units sold or revenue or something. So they do lots of different things, but they have a line of digital signal processors. And if you look down their offerings, it's not so different if you look down other offerings in terms of, they have some fixed point offerings, some floating point offerings, some that do both. So typically if you can do float, you can also do fixed. And what data widths do you see down the column? What's the most common data width down this column?
16.
Okay, down the whole chip set. So this would be 16 is the most common. What's the least common? 24. So again, that's the old Motorola 56,000 family, 80s, from 1980s. Okay, so we got 16 bits, and then for those that are floating point, the most common word size is 32-bit. Right, so there'd be 32-bit float data type. Again, 24 bits of mantissa plus sign, 8 bits of exponent. And you'll see some of these have a 40-bit mode. Okay. So that's analog devices, different clock speeds, but nothing above a gigahertz for their. These are the maximum clock speeds available for their. Freescale, where are they located? Right here in Austin, Texas. They've moved their Palmer Lane facility down to Oak Hill. So they have one major facility now in Oak Hill, southwest Austin. They also have a little bit of operations at Bluestein in East Austin. Okay, so they've been around a long time in this space. So they used to be Motorola, semiconductor product sector, and they spun off and became a corporate entity and publicly traded it in 2004, I think was the official start, but their spinoff took time. So again, you'll see fixed point here, but they used to have a floating point part a long time ago. The 96,000, they've discontinued that. So they're completely fixed point. And they work a lot on automotive, smart grid communications, and so different product spaces. And yes, they have the legacy part here of 24 bits, but most of the rest here are 16-bit processors and multi-core. Microchip, any idea where they are?
California.
You've got a phone? You can look them up. You're Arizona, very good. So we're in Arizona. Chandler, right. And they also have some two fabs. One's in Tempe, and there's another fab outside. I forget where. It's not in Arizona. So they have the PIC microcontroller family, right? So they're pretty high, pretty visible for that. They also have a DSP version of the PIC. NXP, where's that located?
Google it.
Google it. Sure. All right, So will that answer come? So they have, this is a video, this is for video processing mainly. It's a multimedia processor. So you'll see the 8-bit data. The 8-bit data type is that's where you start seeing pixel, right, 8 bits per pixel color, red, green, blue. Okay, so once you start seeing 8 bits, you'll see something that's probably mainly for it's also used for image processing. Okay, so where is NXP? Netherlands, very good. Eindhoven, very good. They used to have a design center in Austin that was sold to, I think, Silicon Labs. Pico Chip, where are they located?
You said Silicon Valley, you mean it to like
England.
So Pico Chip's England. NXP used to have NXP, and then NXP had a joint venture with, I think, STM, and then some part of that got sold to Silicon Labs. So in looking up NXP, I couldn't find an Austin location that they list on their website anymore. So I don't know. Pico Chip, so I heard England. Okay, so England. And that's only a fixed point part. Qualcomm, based where? San Diego, but a lot of the work is done here in Austin for the DSP cores that they do. And again, you'll see, some of these are for, media. You see the 8-bit data type. Texas Instruments, where are they headquartered? Dallas. Where do they do the work on the DSP processors? Yeah, so it's Dallas. So that's a good guess. A lot of the ARM stuff is here. Dallas is a lot of the DSP stuff, plus ARM. And Houston used to do quite a bit of the C6000 work at one point. And there's some work in France. And I think, in Nice or something. There's a TI location in France that was involved in the C5000 and the C6000 development. So lots of parts here, lots of parts to choose from. But if you kind of look at the numbers, they really come into 3 kind of groupings. There's the 2000 family, 5000 family, and the 6000 family. And the rest of these are really subfamilies within those 3 main families. So the 2000 is mainly DSP and control put together. It's also used in smart grid communications, power line communications, for example. This is the old 2G cell phone, also digital still cameras, C5000. And C6000 is everything else. And actually the smart grid stuff is the 2833 family down here. I take the back. No, the smart grid. No, smart grid's up here. It's up in this one. It's a fixed point part. Okay, so this is, and you'll see again. You'll see 8-bit components for media, right, for this processor. You can address 8, 16, or 32. And there's also a 40-bit mode for registers. Okay, last one, Tylera. Where are they based? Right. So Tylera is San Jose. It's an MIT spinoff. It's a direct spinoff of work at MIT. Qualcomm, 2 of the founders were professors. They took their work into the corporate world. Did very well, obviously. And then so that's the chipset part. And you'll notice that a couple other things down this. Do you see any? What's the fastest processors you're seeing in terms of clock speed? Yeah, in the gigahertz range. So here's a 6600 family from TI. It's 1.5 gigahertz in clock speed, and there are 8 cores on this chip. So it's for base stations. So it's 12, billion, whatever, instructions for the C6000 per second. And the C6000 can do, so each core can do 2 multiplies, fixed point, and really 1 multiply in terms of sustainable throughput for the floating point case. That's a lot. It's a lot of crunching, number crunching. But remember, for each cycle, each core can do 8 instructions in parallel. So it's quite a. So I have 8 cores, and then each core can do 8 instructions. It's a lot of crunching. The column here under the next column up here is benchmarking, and the benchmarking has 2 flavors. One, if they actually did it on a physical processor, it's in bold, and if they did it through simulation, it's italicized. And this is and the ones that are italicized are estimates of the simulation benchmark. Higher is better, based on projected clock speeds of the processor through simulation, not through the. And these are about a dozen basic kernels written in assembly. FIR filtering, IR filtering, there's a truth table, there's a convolution, complex FIR. It's just a basic number crunching. Doesn't test the memory subsystem, doesn't test the compiler, doesn't test the operating system. There's a separate benchmark for memory. And last thing is price. And it varies a lot in price. And there are some $2 parts, and I don't know if it shows up as well here. There are some $2, yeah, there it is. There's some $2 parts on the unit price. So they also let you read over the cores. ARM is the probably the most visible one on this list, shipping more than 10 billion cores to date. Okay, we'll see you next time. See you on Friday.